Okay, so I just handed back your quizzes, and I think maybe the one thing that some of you may be wondering about was for the energy balance question. For full credit on that one, I needed to see not only that it's estimating energy, but also like what are the components of the energy that it's estimating. And so the individual pieces of what it's calculating is it's estimating how much long wave radiation is being emitted. It's estimating how much incoming radiation there is after reflection. So just that next step to, it's doing an energy balance, but what is it balancing? So if you have any questions about your grading on that quiz, please feel free to let me know. On Thursday, you've got your infiltration assignment due and also the midterm exam. And so a lot of hydrologic engineering in the next couple of days. Remember that about the equation sheet, you can prepare a one-page front and back equation sheet, but it's not going to be allowed to be used during the concept questions. And so you don't have to take the time of writing down a bunch of vocabulary definitions and whatnot on that equation sheet because you won't be able to use it during the part where you need to understand and describe concepts. Okay, we're going to finish up the material that's covered in the first midterm exam by discussing infiltration today, and that's section 4 of chapter 7. Like I mentioned, we're going to begin with a video that illustrates water movement in soil, and it's kind of interesting, but it also makes a lot of the abstract theory stuff that we've been looking at in terms of diagrams and equations. It kind of brings it all to life. So I feel actually pretty fortunate that we've got this video. It's just one that I stumbled on last year on YouTube from university in the Netherlands. So let's see if we can get that going. All right, so what we're seeing is as there's ponding at the water surface, there's an increase in the water content, but it's not saturated until you go closer to the surface at a certain time. And so the way we're going to represent that in a diagram, there's a figure that shows here a wetting front moving down through the soil. So at a given time, it's fully saturated at the surface, but if you go deeper down, there's just a small increase in water content. And so consider this curve. What it's saying is, as you go closer to the surface, as you go up towards the ground surface, the moisture content is increasing until it gets to saturated. So this curvature is showing an increase in the wetting front. Now here's the water table. So of course, below the water table, it's fully saturated. So the moisture content is equal to the porosity at that point. But as you get away from that, the capillary effect means the moisture content decreases a bit. But then during a rainfall event, when there's ponding at the surface, the water penetrates not all at once. It doesn't go from like normal water content to fully saturated. There's this curvature here, like a gradual increase. And that's what we're seeing in this video, is we're saying that it may be saturated at this point, but this isn't fully saturated. If it was, it would be penetrating through the sand, because we see what happens when the voids are fully saturated. The sand immediately becomes like a highway for that water to pass through because it has such a high hydraulic conductivity. So that hydraulic conductivity effect doesn't kick in until saturated conditions. So I just wanted to pause. We'll continue finishing the video there. But that's an important point, and I also wanted to tie it together with these figures that we're going to look at. And these figures seem abstract when you just see them for the first time and you're not able to kind of relate it to this visual representation of the water penetrating down through the soil. So what we're seeing is the wetting front go downward and outward because of gravity and because of the suction/tension within the soil. So those are the two things that are bringing the water down. But then the difference between full saturation and just an increase in moisture. All right, so in the video she talked about the movement of water when it's under pressure and the movement of water when it's under tension. And water is under pressure when it's fully saturated. So consider the water table. I think we had a figure on a previous lecture. Let's see if I can find that one. Yeah, here. All right, so here's the pressure profile where we're down below the surface, and then here's the water table. So if you go below the water table, then the water exists under pressure, and it'll move one way. But when you're above the water table, in the capillary fringe, there's water that exists under conditions of tension, meaning that the attraction for the soil is sucking the water grains away from one another, and so that it's making space between the soil grains for those voids to have air in it in addition to water. And so the movement of water is different if you're below the water table, meaning saturated, or above the water table, meaning unsaturated. But we don't only have unsaturated flow in that capillary fringe. The unsaturated flow also occurs during a wet weather event as the water penetrates downward through the soil. So just as a refresher, remember that we have under the soil voids that are containing some water and some air. And this illustration is showing that we have solid particles that are covered by a thin layer of water, and then in the space between those thin layers of water, the air exists. And the smaller the grain, the more tightly bound the water will be to the solid particle, and the higher the suction or the tension will be when we have unsaturated conditions. Okay, so here's this figure that I already kind of showed you, that under ordinary conditions, the moisture content decreases as you move upward from the water table until you come to some like initial moisture content prior to a storm event. But then as water ponds at the ground surface, then the wetting front moves downward through the soil. And the speed of its movement depends on the gradient between the initial moisture condition and what it will be at saturation. It depends on the hydraulic conductivity of the soil, and it depends on how deeply ponded the water is at the surface. So there are a lot of things that affect how quickly the water is going to penetrate down. And so what we need is some sort of an equation that accounts for those factors, like an empirical equation that allows us to predict how quickly the water goes down. And why? Why do we care about all this? Remember, the rainfall that hits the soil has two places to go, broadly speaking. It can either go into the soil or it can go over the surface towards some point of concentration, towards a watershed outlet. So runoff equals rainfall minus infiltration is the broad way of looking at it. So during a rainfall event, as there's ponding at the surface, then the soil capacity to absorb water decreases. The rate of infiltration declines over time because there's going to be a smaller driving force. The initial driving force, what we saw is that at first in those videos, the water penetrated downward and sideways very quickly because there was a lot of suction. But then as more of the grains become filled, there's a smaller driving force that that suction or tension head decreases. Okay, so this is what happens during infiltration. At the surface, the voids are completely saturated because we assume that there's a little bit of ponding at the surface. The water is distributed into the soil grains completely, and so this curve of moisture content goes from fully saturated, and then there's this transition zone that's a lot like the capillary fringe. In the same way that there was kind of like the standard water concentration and then some connecting the curve between fully saturated and the middle ground where partially saturated. So this curved zone here, it's kind of like we've reversed that, and now this transition zone is the equivalent of the capillary fringe. And so some of the voids have small diameter, some of the voids have big diameters, and the split between the two affects the shape of that transition zone. This is a really complicated curve for us to be able to model directly. And so instead of modeling it directly, the Green-Ampt method, which is the most sophisticated of the two methods I'm going to share with you, says that we're going to have to assume the wetting front moves as a solid wave, that this transition zone is kind of neglected, and so that is one of the limitations of Green-Ampt, is that it assumes that you go from immediate transition of the initial moisture content to fully saturated. It's modeling saturated flow rather than unsaturated flow. But in spite of that, it does a pretty good job of describing the curve of declining rate of potential infiltration.
So let's just say what on the both sides represents going from partially saturated to full saturated?
Mm-hmm. Yeah, so here is fully saturated. This vertical line means that as you go down through the soil, the moisture content stays the same. And then this is the zone that hasn't been affected by the rainfall yet. So there is a zone of saturation, but then the transition zone is where there's a little bit more water than there was originally before the storm, but there is also some air in the voids. And so this is the unsaturated flow, which is associated with the transition zone. Austin?
So this is assuming that the water table is below all this, right?
Yeah, the water table would be below this and not shown. That's right.
So the line itself, like the data it's representing, is that the flow or is it like the moisture content?
It's the moisture content. Yep. Yep. And so here in Green-Ampt, it's saying unsaturated flow is too complicated. Let's throw up our arms, give up a little bit, neglect this curved region, and just try and predict how quickly the water's penetrating based on saturation. And so if we think about what's really going on, and it can be thought of in terms of the Darcy's law. Remember, Darcy's law is the hydraulic conductivity and then some cross-sectional area that the water is flowing through, and then the driving force, where H1 and H2 is some elevation gradient between the upstream and the downstream location, and then L is the length over which the flow occurs. Well, the Green-Ampt simplification says let's use those same kind of ideas. Now, instead of doing it on a volumetric basis, let's just take the area parameter out. So if we took the area parameter out of Darcy's law, then it would have units of length per time instead of units of volume per time. So if it was just K times H1 minus H2 divided by L, it would say the speed that the water is moving through the column of soil. And that's what this Green-Ampt simplification says, is it says let's measure the driving force. And the driving force is the depth of ponding at the surface, so that's H naught. That's, you can think of the water being pushed from above. And then the second term is how much the water is being pulled from below. So it's the suction. Psi is the symbol. We looked at a table of different types of soil and how much suction they have, where clay has a lot of suction, a loam would have slightly less, sand and gravelly soils have an even lower suction head. And so the more this length expands, that's going to result in a decrease of the total overall suction. When this L is very small, there's a lot of suction capacity because you've got a big depth of soil and all of it is eager to receive the water with a really high tension. So over time, as the wetting front penetrates deeper, the driving force decreases. As the length increases, then the driving force decreases, and so the infiltration rate slows down. So this lowercase f has units of centimeters per second. It's a rate or a speed, the speed that the water is moving down through the soil. If we integrate that over time, we want to know the cumulative infiltration that's occurred to a certain point, then that's uppercase F. And the way that that's modeled is just by looking at the rate of infiltration over time and integrating that from the start of the rainfall event up until T, the time in question. And this figure kind of shows both the declining rate of infiltration and then the increase in cumulative infiltration, but also it's beginning to plateau and it'll eventually reach some maximum value that it doesn't go above. So look at the rainfall. Initially there was a pretty high rainfall intensity, then the rainfall decreased a little bit, but in each of these cases, the rate of rainfall was greater than the infiltration rate. So that means that there's going to be ponding at the surface. There's more water at the surface than can be absorbed by the soil. And the Green-Ampt simplification requires that. It won't be accurate. It'll be even less accurate than usual if we don't have ponding at the surface. So that's one of the things that I have to tell you, is that the Haito graph of rainfall needs to be above the infiltration curve for us to have any hope of accuracy. And essentially what we're seeing is a column of water penetrating down through the soil, and there's this immediate increase from the initial moisture condition to full saturation, where L is going to be, over time, the length that that water column penetrates down into the soil. So we could know what's the cumulative infiltration amount by looking at how much of the pores filled up. Like the volume of water that was absorbed is going to be the initial moisture content minus the overall porosity minus the initial moisture content. And so that's kind of like a fraction, remember, a storage fraction. So it went from fully saturated, when the water penetrates all the way down, so the porosity is totally full with water. So the physical length of this soil, like if the wetting front goes 10 centimeters, it's not that it was 10 centimeters of actual water that was infiltrated, because remember, some of this depth is occupied by solids, and there was some water there to begin with. So a 10 centimeter L does not mean that there was 10 centimeters of rainfall. 1 centimeter of rainfall may cause L to be 3 centimeters, or even more if there was a pretty high moisture content to begin with. But I just wanted to point out the difference between the penetration depth is not the same thing as how much was actually infiltrated. Just because it's a matrix of, we go back to that figure, to begin with, there is solids and some initial water. So the volume between here that's filled with air initially, that's the only place that the incoming water can go. And so if we have 1 unit of water, it's going to infiltrate much deeper than 1 unit of depth. Okay, so here's the Green-Ampt equation. And to try and make sense of it, we're going to go through a spreadsheet calculation. Remember, lowercase f gives us a rate. So that'll be the infiltration rate. And it depends on the hydraulic conductivity. It depends on some soil properties. And so psi here, the suction head, is something that we'll look up off of a soil property table. But the thing that makes this tricky is it's an implicit equation. And you remember those from hydraulics, where the unknown is both on the right side and the left side of the equation. And so here you can see when we're trying to calculate the cumulative infiltration depth, you can see that the cumulative infiltration depth is on the left side and the right side of the equation. And so our approach to that was that we made some guess of what it might be, and then we checked the right-hand side and the left-hand side, and we keep adjusting our guess until the two sides of the equation are equal. We had to do that with the Colebrook equation for friction factor F. So we'll be doing a similar thing here for Green-Ampt. We'll be using a similar approach to find out what is the infiltration depth and the infiltration amount. Now remember that the increase in moisture content, if we look at the increase in moisture content from a graphical perspective, the initial moisture content is just this theta sub I, and then saturation is the overall, where the moisture content is equal to porosity. And so this delta theta on this figure is the difference between fully saturated voids, where water is in all of the spaces, and the initial amount of moisture that was there before. And so how much the moisture increases, the delta theta goes into the equations for both infiltration depth and infiltration rate. So we'll have to calculate that by looking at the effective saturation and the effective porosity. So the method is, in the example we're going to work, we're going to be given the hydraulic conductivity of the soil, which is a soil property that you can experiment with and determine directly. We will be given some time frame that we want to know how much infiltration was there during maybe the first 20 minutes of a storm, because we'd want to know how much runoff there was during that same period. So we'd need to look at infiltration to know what kind of runoff there was. And then we can look up the soil property of the suction head, and then the change of water content is, we're going to have to understand how much water was in the soil initially to be able to know the potential for the increase. And then we'll try some guess value of the infiltration amount on the right-hand side, and then as a starting point, you'll notice that there's two terms. There's the hydraulic conductivity times the time, and then this secondary part of the equation. So just as a guess, we might as well calculate directly K times T. And then we'll keep playing around with this guess of F sub T until the left-hand side and right-hand side are equal. Now here's the table that's in our book for Green-Ampt parameters that can be used for different types of soil. And so it has ranges of porosity as well as some typical mid-value. It's got ranges of effective porosity as well as a typical value, the suction head for these different types of soil, and then typical hydraulic conductivities. And so in the example, we'll just use these default middle values for the soil type that's described. Now if we look at the trends, if we go from sand to clay, remember what we saw in the videos, is that when there's saturation, the water moves really easily through the sand, and that's because of the high hydraulic conductivity. So for saturated flow, sand is great. But the reason when sand wasn't so great was when we had unsaturated flow. And the reason for that is look how low the wetting front soil suction head is that the sand doesn't really draw the water in. It serves as a good conduit when there's pressure, but the sand itself doesn't suck the water downward in the same way that finer particles like clay and silty clay. With this high suction, wetting front soil suction head, that's when we saw the pretty rapid unsaturated conditions. It accounted for a rapid increase in the movement of the wetting front. So the soil suction head goes the opposite of hydraulic conductivity. It increases in the direction of sand to clay. So the clays have more suction. So the driving force is going to be the difference between the soil suction and the penetration depth, L. Now effective porosity. Let's look at effective porosity. The porosity versus the effective porosity, it's pretty close for sand, but then for clay, the porosity and the effective porosity are further apart. And the reason for that is that the clay is going to retain more water, that gravity isn't going to drain clay soils as well as it will drain sandy soils. All right, so let's try this example here. I don't think I gave you a template file. I think that we're going to have to just create this one from scratch, but there's not too many moving parts, and so that's all right. We've got a silty clay soil with these physical properties, and we want to know the infiltration depth and the infiltration rate after 1/10 of an hour and 20% of an hour, assuming initial effective saturation of 20% and continuous ponding. We'll just do some initial stuff on the whiteboard, looking at how to calculate the delta theta, and we'll also calculate the time to ponding, because we're going to need that a little bit later. Before we move into the spreadsheet, we'll calculate some of these things on the whiteboard. Okay, so first of all, the psi suction 29.22 centimeters for this soil. The hydraulic conductivity is 0.05 centimeters per hour. The initial effective saturation is 20%, so that is S sub E is 0.20. Effective porosity 0.423. I think I may have done my example at a different initial saturation. So let's change the, my calculations are based on an initial effective saturation of 45%. So please scratch that out in your notes. Okay, so S sub E is 0.45. I'm not sure why the discrepancy there, but I'm glad I caught it now rather than later. So delta theta is 1 minus S sub E times theta sub E. So that is 1 minus 0.45 times the 0.423. So that tells us that the water is going to increase 0.23265 as it goes from the initial water content to fully saturated. That's how much storage capacity the water has on a per unit volume basis. So right now, the voids are mostly, well, the space is mostly full with soil particles and existing moisture. So only 23% on a volumetric basis, 23% of that volume is available to absorb new water right now. Okay, so let's look at how much infiltration depth there is and also the infiltration rate over time. So we'll start up Excel here. Did I give you guys the template file? No, okay. Let me do that. I can make that happen fairly quick. You don't have to necessarily use it, but it'll be there if you need it. So our effective porosity was 0.423. The suction head was 29.22. The K value was 0.05. The S sub E, 0.45. And then the delta theta, 1 minus S sub E times SE. All right. And the example is asking what happens after 0.1 hours and 0.2 hours. So let's have 0.1 hour and 0.2 hours. We want to know what was the infiltration depth and what's the infiltration rate. I'll give you a moment in case you need to get that file. Most of you have already been able to download it. Okay, so infiltration rate. We have to start with a with a guess. And so it said that an initial guess might be k times t. So let's just have that as our first guess here. T times k. So here's our initial guess of the infiltration depth. Now the right-hand side of the equation that we're going to be typing in is the right-hand side of this equation. Okay, so right-hand side is k times t. So k, I'm going to anchor that so I can drag it down later, times t plus psi anchored times the delta theta, anchor that as well, times the logarithm of 1 plus, now where it refers to the f of t, we'll put in our guess value, which was in cell B10. I can't click on B10 because my formula is centered and it's getting in the way, so I'll just type in B10. Okay, and then that is divided by psi times the delta theta. I'll leave that up for a moment. Okay, now this column is the difference between the two. So the one on the left minus the one on the right, or vice versa, it doesn't matter. But the reason why it's useful to have this difference column is our objective is going to be to minimize the difference by changing this guess value of the infiltration depth. Now, you notice this note here that in some cases goal-seek may not be good enough. And the reason why is that we're working with small numbers, and goal-seek sometimes quits when convergence is just kind of like most of the way there. But solver, you can adjust the convergence criteria. You can tell it, like how many digits it has to match before it assumes the solution is finished. And so I don't know if solver is even on here. It looks like it's not turned on yet, so I may have to install that. I think it's in maybe like the options, add-ins, manage Excel add-ins, go. Okay, click solver, and then hopefully it'll show up over here. There it is. Good, good, good. So if you don't have solver, the way to get it is go to File, Options, Add-ins, go Manage Excel Add-ins, and then click Solver, yes, click OK, and then it'll show up over here. All right, so what we're going to do is start up Solver, and we want the objective is the difference is equal to a value of 0 by changing this guess value of f of t, and then click Solve. And the reason, again, why we're doing solver instead of goal-seek is we could choose these options here, and in the options you can say the precision you want for convergence. And sometimes goal-seek is okay, but in the past I've had solutions that didn't quite work out because goal-seek wasn't using a fine enough precision, whereas with solver we have direct control over that. So once we say solve, then it goes and solves for the infiltration depth.
Which cell do you change? Just one of them or both? In the solver?
Just B10, just the guess value of f of t, because everything else in here in this formula is known. What makes it implicit is the f of t. So let me put up the formula for the right-hand side again. So it's k times t. So here's the k times t. T is the only reference in here that's not anchored except for the reference also to the infiltration depth, the guess value. Anybody else also get 0.264?
Can you go through the solver again and what to put in?
Mm-hmm. Yep. All right, so we have some guess. Maybe our initial guess value was, I can't undo. Let's say it was 0.05. So there's a difference here. It doesn't work. So what we want to do is have the solver set the objective. Our objective is the difference between the left side and the right side is 0. So set objective to a value of 0 by changing this guess left-hand side of the solver. And click OK. And then keep the solution. So then the infiltration rate we can calculate directly. So the infiltration rate is going to be K times suction head times the delta theta. I guess I probably ought to anchor all these references so that when I drag it down to the next time step, it'll be useful. Divided by our infiltration depth at this point in time, plus 1. So here's our infiltration rate. Before we drag it down, let's do a reasonableness check. What we're expecting to see is a declining rate of infiltration over time. The Green-Ampt model is trying to say, over time, as those voids get filled up, the driving force is going to decrease, and so there's less tension sucking the water down from above. So the infiltration rate shortly after the storm starts should be higher than the infiltration rate later. So that's the reasonableness that we need to be on the lookout for when we solve for time step. Time is 0.2 hours. We're hoping that the infiltration rate went from relatively high to a bit lower. So let's see if that's the case by now dragging down from 0.1 hours. I just put in some guess here, 0.1. I'm going to have to, I can drag the formula down, but I'm going to have to goal seek again a second time. Okay, so let me do, again, the goal seek where I'm using solver. I guess I shouldn't call it goal seek if I'm using solver. Set the objective to the difference is equal to 0 by changing this B11, so our new infiltration depth. Click solve. Okay, so it's got more infiltration depth, and then we directly calculate the infiltration rate, and it's lower. So it matches reality. What we know from reality is that the deeper the water gets into the soil, the infiltration rate is declining. So it's a declining rate of infiltration over time during the storm. The longer the storm goes on, the water becomes less and less hungry. The soil becomes less and less hungry for the water. I guess the better way to say it is that the tension decreases as the soil column becomes saturated.
For the first calculation of infiltration depth,
Mm-hmm.
we just take the T divided by K, like that's the
Oh, the initial guess?
Yeah.
Yeah, the initial guess was just K times T. But we don't have to sweat it. If you put anything in there, then solver is going to eventually be able to converge. It just converges a little faster if you start with a reasonable initial guess. Are there other questions about this? Okay, so that's the Green-Ampt method. Ponding time is another factor that comes up. And remember, there's the potential rate of infiltration is high, but the rainfall rate may not be as high as the potential infiltration rate. This is important. Do you need more time to work on the spreadsheet? We can pause for a moment if you need more time on it. You got it? All right. Okay, because this is important conceptual stuff here. So just keep in mind that sometimes it's not raining as hard as the water could be absorbing, as the soil could be absorbing the water. So in other words, the infiltration capacity of the soil can be greater than the rainfall rate. And so it's not necessarily called the direct infiltration rate, it's called potential infiltration rate. And it only becomes the actual infiltration rate if there's ponding at the surface. And so we can say that when the rainfall rate is equal to the potential infiltration rate, that intersection between the two curves is when the ponding occurs. And that's when it goes from a potential infiltration rate to an actual infiltration rate, is after ponding starts. So you can see this field, when it started raining, remember the typical pattern for a storm is that at first it's just a few sprinkles. And so if it takes a while for the storm to get started, then you're not going to have the full infiltration capacity of the soil satisfied from the very beginning of the storm. Even if it's a constant rainfall rate, like this is showing a constant rainfall rate, there's still some period beforehand where the infiltration rate is greater than the rainfall rate. So if we look at it, this was in terms of rate. If we look at it in terms of depth, so capital F is depth, so the cumulative amount, the cumulative rainfall, when it comes into contact with the cumulative infiltration, that is T sub P, the time to ponding. And so you can know the time to ponding, it's the rainfall intensity I times T sub P will tell you the depth that has infiltrated at the ponding time. So this shows how to calculate T sub P. So let's do this on the board here for the example that we've just been working. The time to ponding, where we had all of these factors that are shown on the board here. The formula is going to be K psi delta theta I minus K. Now I was the the rainfall intensity. So it was 1.5 centimeters per hour. So if we have a rainfall intensity of 1.5 centimeters per hour, how long until ponding occurs? So I'm going to say I is 1.5 centimeters per hour, just constant to keep things simple. So for part A, let's find out the time until ponding occurs. So we'll just substitute in these values here. The K value is 0.05 centimeters per hour. The suction, 29.22 centimeters. And the delta theta is 0.23265. And now I, 1.5 centimeters per hour. And then the difference between I and K, 1.5 centimeters per hour minus 0.05 centimeters per hour. So you can calculate the time of ponding directly. It's 0.156 hours. So that means that with this particular soil, you'd have to have a constant rainfall intensity of 1.5 centimeters per hour for about 9 minutes. This works out to 9.4 minutes. It wouldn't be until 9.4 minutes that there's ponding at the surface. And so the total infiltration depth is going to be a little bit less than is predicted by the Green-Ampt method, because the Green-Ampt method assumes that from the beginning of the storm, there is ponding at the surface. But what this shows is that you don't have instantaneous ponding. And so one of the limitations of the Green-Ampt method, remember we talked about it's assuming that there is this constant block wave of going from initial moisture content to fully saturated. And because of that assumption, it's going to be a little bit inaccurate. And one of the inaccuracies is that it overestimates the infiltration amount because it requires initial ponding at the surface. But there's going to be some time period that it takes before the ponding occurs. So this kind of helps you to see how big the deviation is between the assumption and the reality. And the time to ponding is part of that. So what rainfall intensity would cause ponding after 20 minutes? So now, if we wanted to find out what rainfall intensity is going to cause ponding after a different amount of time, so in the first part we said 1.5 centimeters per hour. What if we don't know what the rainfall intensity is, but we know that we're talking about a T sub P of 20 minutes? So that is a third of an hour, 0.333 hours. Then I equals what in a situation like that? So the way that we can solve this is it's going to be rearranging the equation to solve for I. The same T sub P equation, but if we solve for I, then that's I squared minus I times K. On the left side, the right side is K times psi. Delta theta and T sub P. Okay, so that is 0.05 centimeters per hour for the hydraulic conductivity. Psi is 29.22 centimeters. And the delta theta is 0.23265, which we calculated at the very beginning. Now, naturally, the time of ponding of 20 minutes is going to require which intensity? So we have this known 0.333 hours down in the denominator. So this means that I squared minus I times K is 1.0207. That's the result of all of this. And so now we have an equation that we need to solve the roots for. It's going to be I squared minus 0.05I, because K is known, it's the hydraulic conductivity, minus 1.0207 equals 0. And so the roots of that equation is, one of the roots is negative 0.986, and the other is 1.036. So obviously it's the positive root, so that's centimeters per hour. It takes a rainfall intensity of 1.036 centimeters per hour would cause ponding in 20 minutes. Does that make sense with what we saw before? Well, what we saw before is that a higher intensity, 1.5 centimeters per hour, would cause ponding after 9 minutes. So this kind of does match the trend that if you have a lower intensity, that the time to ponding will be greater. And then finally, to calculate the cumulative infiltration during a certain time, we would just substitute those values into the formula for F sub t. We've already done that, so since we're running low on time, we won't do part C since we've already done a calculation similar. We've got 2 minutes till time is up for class. I want to tell you about one other method that's easier. It's a lot less sophisticated, but the Horton model just is an empirical representation of the shape of this curve, and it's based on observed behavior in different types of sand and loams and clays and so on, where you look up the minimum infiltration rate. That's what this F sub C is. It's like as low as it gets. And then the initial infiltration rate, and then tries to connect the two with a curve. So the intercept is the starting infiltration rate. F sub C is kind of like the gravity infiltration rate after all of the suction is exhausted and it's just flowing downward due to gravity. And then as a function of time is using this K value to connect the two. And so you can use the Horton model to know the infiltration rate by substituting in these given parameters, and then to find the infiltration depth as a cumulative integration of the infiltration rate, you're multiplying the initial by what time it is. I'm sorry, that F sub C is the minimum. So F sub C is the minimum, just a different formula that is used to predict the curvature of the declining rate of potential infiltration. So it's less sophisticated than Green-Ampt, but it's easier to use if you've got these soil parameters for the area of interest. All right, well that's it for today. I'm sorry that we had to rush through these examples a little bit, but I hope that the videos that we watched at the beginning of class was useful to help you understand and kind of visualize what's going on beneath the surface. If we look at these announcements, it's the homework and the exam. If you've got any questions about either, please feel free to stop by during my office hours or send me an email and I'll do my best to respond. Otherwise, bring your equation sheet and your calculator and your computer. You know, everything's fair game, so don't rule anything out as far as the computer goes. I'll see you on Thursday.
Will that cover up to what's covered today?
Yes. Mm-hmm.